Hello everyone, I am Rahul Kumar working with Professor Sundaresan at Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, India. I will be talking about possibility of quantum spin liquid state in a one-dimensional magnetic chain. Coming to one-dimensional magnetic chain, it is generally characterized by J1 and J2. J1 is nearest neighbor in exchange interaction. J2 is next nearest neighbor in exchange interaction. Generally, depending on the ratio of J2 and J1, the magnetic ground state can be nil, antiferromagnet, spin liquid, or dimer state. But if you see in the literature, most of these systems are based on copper ion or 3D ions, but there are very few reports on 4F systems, and also they are getting ordered at lower temperatures because of the dominating value of J1. So the region of this can be the localized nature of 4f orbitals, because of which you will not get the significant value of J2, and we can't get access to the full phase diagram which is shown here. But in case of 3D orbitals, you can have a significant value of J2 also, because of the significant overlap of the wave functions. Now, considering this problem, I thought let's explore a one-dimensional system with a 4F ion to see whether we can get access to a whole phase diagram or not. So I have prepared a new YB chain compound NaYBT27, which crystallizes into a monoclinic space group, and this is the unit cell. You can see the YB ions are making a one-dimensional or quasi-one-dimensional magnetic chain along the B axis, which is widely separated along C axis. And please note that these YB ions are having polyhedra, which is edge shared, and there are two different angles for the exchange interaction. The difference is around 6 degrees. This difference is very significant. That will I will discuss later. Coming to its magnetic properties, we have done the magnetization measurements down to 400 millikelvin, and we didn't see any magnetic anomaly which may show long range magnetic ordering. Further, we have done isothermal magnetization measurements down at different temperatures. At lowest is 400 millikelvin. So we find out that at lower temperatures the curves are deviating from Brillouin function. So Brillouin function generally describe the paramagnetic nature of a compound. If it is deviating, that means there are some magnetic correlations are present, and since it's deviating below 1 Kelvin, which means the magnetic correlation are roughly of the order of 1 Kelvin. Now coming to inverse susceptibility data, you can see there are two linear regions separated by a crossover. I have fitted both the linear regions with Curie-Wiesla and found that there is a reduction of magnetic moment, effective magnetic moment for YB ions, uh, and also the value of theta is also decreased because of the change in value of J. So here it is an indication that J is not constant, is getting changed, and so we can't use the simple Curie-Wiesla. So I have used modified Curie-Wiesla with two-level approximation and find that it could fit the whole range of susceptibility data quite well. And you can see this is the energy difference between ground state and first excited state. This is a typical splitting of electronic state for a YB ion. You can see with spin orbit coupling, it's still in J equal to 7 by 2 state. You get crystal electric field splitting, and being a Kramers ion, it will split into 4 Kramers doublet, total 8 states, but the ground state can be described by J effective equal to 1 by 2 state. So from these measurements, we can say it is not getting ordered down to 400 millikelvin, and its ground state can be described by J effective equal to 1 by 2. Coming to heat capacity measurements, we didn't find any lambda kind of anomaly down to 280 millikelvin. It would have been characteristic of a long range magnetic ordering. Further, if you see the magnetic entropy under uh, high magnetic fields more than 5 Tesla, it is approaching to RLN2. It is again telling the ground state is J equal to 1 by 2. Now, if you see when we apply magnetic field, there is a Gman splitting, and because of which we can observe a Schottky anomaly in this system, which moves in temperature with application in magnetic field. So I have single out the Schottky contribution by subtracting the zero field data and then fitted it with two level approximation and find that the internal magnetic field is around 1 Kelvin, which would have been zero in the if there is no internal magnetic field in the system. So this again reaffirms our magnetization measurement where we have seen magnetic correlation up to 1 Kelvin. Further, if you see the low temperature magnetic heat capacity data, you can see there is an anomaly around 0.55 Kelvin. Uh, but if you see the magnetic entropy, it is around 60% of the theoretically expected magnetic entropy, which means it may not be related to the long range magnetic ordering, although it is due to widespread density of state as in YB and GaO4 compound. Considering the presence of Schottky anomaly in heat capacity measurements, we have carried out thermal conductivity measurements also, because in these measurements you will not have any contribution from or kind of Schottky anomaly. So we find that these measurements are mostly field independent on this sample, and the low temperature thermal conductivity data could fit it well with this low temperature approximation. In this approximation, the first term tells about the contribution from fermionic uh, kind of excitations. So in this system, since it is an insulator, we can't expect this contribution is coming from electrons. So it may be the magnetic excitation which are scattering the phonons at that temperature. Further, if you see the field dependence of the value, it is increasing and decreasing, means it's not constant with magnetic field. That means there are some magnetic excitation which are giving rise to phonon scattering at that temperatures, further reinforcing our uh, uh, magnetization and heat capacity results. From all these measurements, so there are some conclusions. First one is the system is low dimensional magnetically and ground state can be described by Z factor equal to 1 by 2. Second thing is there is no ordering down to 280 millikelvin despite is having theta value of minus 1.49. So frustration is around 5. And further, all the measurements have indicated the presence of magnetic correlation of the order of 1 Kelvin. Now, as I told earlier, it is this one-dimensional chain compound also based on 4F system, 4F ion YB3 plus ion. So we may not have J2 that much significant. Then what is the driving force behind this such kind of correlated state? So one possibility is the presence of different exchange interaction between nearest neighbor YB ions. You can see there are two different angles, 107 degree and 113 degree, and those are also alternating. So there is a recent paper on like titled as frustration and anisotropic exchange in ytterbium magnets with edge-shade octahedra. As I told earlier, these polyhedra are also edge-shade and it's YbO7. So if you consider the just take an example of 97 degree and with seven ligands, can see the ratio is 0.44. But if you go for the 4-degree chains, 101 degree, and see the 7 ligands, but the value is almost half. This ratios become almost half, which means this change in the bond angle is playing a crucial role in determining these values. This is very intriguing, that this small change in bond angle can result into such huge change in the ratio, and because of this, uh, we may have the competition between these action interaction and can get such correlated state. So it may be a quantum spin liquid state, but further investigation is required using local probes such as musr and inelastic neutron scattering. And as I told, most of the rare chain compounds orders at lower temperatures. It may be the first to show such behavior. Again, the more investigation is required for this compound. So thank you for your kind attention, and I leave you with the very nice photos of our magnificent campus. Thank you.